Welcome back to the deep dive. You're here because you need knowledge, and you need it fast, applicable, and clear. Today, we're really getting into the difference between just being a coder and being an architect. You know, the difference between code that just works and code that's actually good, robust, scalable.
Exactly. And we've boiled your sources down to two really fundamental practices. They're critical for any modern code base, but especially in C and C++ ANR. First is refactoring. That's all about improving the internal quality of code you already have. And the second is header files and project layout. So that's more about managing the external structure so the whole thing doesn't collapse as it grows.
So our mission today is pretty straightforward. We want to give you the shortcut. We're going to distill that professional playbook for maintainability, for collaboration, and, for efficiency so you can build software that actually lasts.
Yeah, and if you only take one thing away from this deep dive, it should probably be this. Refactoring makes the code better without changing what it does on the outside. It's a purely internal job. Headers, on the other hand, and the whole architecture they enable, that's all about organizing the project externally. It's about managing that inevitable complexity. They enforce that critical separation of the what from the how.
Okay, let's unpack that. Let's dive right into refactoring. So we're defining it as, what, just restructuring existing code without changing its external behavior.
That's it. It's only about improving things like readability or reducing complexity, the non-functional stuff.
Okay, but let's be real for a second. A deadline's looming. Refactoring is always the first thing to get cut, right? If the code already passes all the tests, why should you, the listener, spend hours cleaning up something that technically already works? How do you even sell that to management?
That is a most important question. And the answer is all about the long game.
Yeah.
You refactor today to save, literally 10 times the hours you would have spent debugging or trying to add features tomorrow. We can actually group the benefits into, say, 8 pillars that justify making this a mandatory investment.
8 pillars. Go.
So pillars 1 through 6 are your direct efficiency gains. You've got improved readability just from clearer names and structure, reduced complexity, breaking down those huge monolithic functions, reduced code duplication, which means more reuse, easier maintenance, enhanced collaboration, so code reviews are smoother, and finally, better testing.
Because smaller focus functions are just easier to write tests for.
Exactly.
So those all make sense. They're about human efficiency. But I'm kind of stuck on pillar 7 you mentioned. Increased performance. How does cleaning up variable names and moving code around accidentally make my program faster? That seems counterintuitive.
It does. But that's where the subtle architectural insight comes in. You aren't necessarily finding a faster algorithm while you're refactoring, but the process itself, it naturally forces optimization. For instance, when you break a massive function, or maybe a huge class, into smaller, more focused pieces, you often improve something called cache locality.
Cache locality? What's that?
Right, so when the CPU runs smaller chunks of code that are physically close together in memory, it uses its own super-fast cache much more effectively. Less jumping around the code base literally means better performance and lower latency, even if you weren't trying to optimize.
Huh. That is genuinely interesting, kind of a side effect benefit. And the 8th pillar is just about fixing the symptoms of bad design, fixing bad structure.
Right. Refactoring is the tool used to eliminate those dreaded code smells. If you've got a 1,000-line function or a class that's doing graphics and physics and networking, that classic God object, refactoring is how you systematically break that down. It turns reactive debugging into proactive engineering.
Got it. So refactoring helps the engine, the inside, run smoothly. But if the engine is perfect and the project structure is a tangled mess, you're still in a maintenance nightmare. And that takes us from the internal details to the external framework, header files.
Exactly. When you're just starting, you can get away with forward declarations at the top of a single file. Sure, but the second you have 3 people on the project or your program hits 100 files, that single file strategy just implodes. You absolutely have to have that separation of concerns that headers provide.
And this is where that crucial nugget you mentioned comes in. You have to think of files as having very specific, distinct roles, or you're just lost. Maybe an analogy would help here.
Okay, think of it like a restaurant. The header file is the menu you give to the public. It's the interface. It tells everyone what exists, what functions are available, what classes, what structs you can use. It's just declarations.
And the source file then is?
That's the kitchen. That's the implementation, the .cpp file. It contains the actual definitions, the recipes for how the code works. This division makes the project manageable, readable, and just fundamentally easier to debug because if something breaks, you know exactly which implementation file holds the problem.
And practically, I mean, for a big team using Git, this must prevent so many merge conflicts because developers are working in separate implementation files, even if they're all using the same header interface.
Precisely. And let's be super clear about the rules here. Headers, your .h or .hpp files. They contain declarations, constants, struct definitions. They must not contain executable code or function definitions, ever. The implementation files, the .cpps, that's where you define those functions. And critically, they must include the header file they're implementing. That's how the compiler connects them.
Right, and the include syntax itself is like a little roadmap for the compiler. We use double quotes for our own files, like player.h, because those are local to our project. It tells the compiler to look in our project directories first.
Whereas the standard library stuff, like IOStream, uses angle brackets. That tells the compiler to look in the system's predefined locations. It's a subtle but really important piece of communication that defines the search path.
Okay, let's talk safety. The risk of multiple inclusions. I mean, pulling the same header into different source files can create just a massive, unreadable compiler error. How do we make sure a header only gets processed once?
We use include guards. This is absolutely mandatory for every single header file you write, no exceptions. You use preprocessor directives to wrap the content. The standard old-school method is that triple check. Hashtag ifdef header file in a at the top, then hashtag define header file in a, and then hashtag endif at the very bottom. The preprocessor just checks if that unique name is defined. If it is, it skips the entire file.
That seems a little complicated, especially if you have dozens of headers. Is hashtag pragma once really the universal lifesaver, it sounds like?
It genuinely is. Yeah. Hashtag pragma once is so much simpler. It does the exact same thing, preventing multiple inclusions, and it's supported by every major modern compiler. A lot of professional code bases just prefer it now for its brevity.
Okay, now for the part that I think trips everyone up, the compiler reality check. If the header files aren't actually compiled and we're only compiling the .cpp files, how does the final program get put together? I mean, if file1.cpp calls a function that lives in file2.cpp, how does the computer know where to jump?
That is the critical distinction between the compiler and the linker. It's a two-step process. When you run a command like g++, file1.cpp, file2.cpp, main.cpp, the compiler doesn't just build one executable right away. First, it compiles each .cpp file one by one into something called an object file, usually a .o or .obj file.
And that object file has the machine code for that one specific file, but it's got holes in it, right?
Precisely. It has holes where functions defined in other files are called. The compiler knows the function exists because it saw the declaration in the header file, but has no idea what its final memory address will be.
And that's where the linker comes in to finish the job.
Exactly. The linker is the final step. It takes all those separate object files, connects them, resolves all those external calls. It fills in the holes at the correct memory addresses and produces that one single final executable program. Understanding that two-step process compile, then link is the key to grasping why headers must only contain declarations.
So we've mastered the internal quality, and we've mastered the basic file separation. Now we need the map that holds it all together. Architecting for success. We're talking about that structure you mentioned, the Pitchfork layout.
We are?
The Pitchfork layout, is it just a cute name, or is the analogy actually meant to help us remember the structure?
It's a very helpful visual, actually. Think of the handle of the Pitchfork as your core source code. And the tines are the exposed interfaces, the public APIs that other people use. It visually reinforces that core practice, separating your public interface from your internal implementation, even at the directory level. Honestly, when you present a project structured this way, it immediately tells a hiring manager that you understand professional-level scalability.
Okay, so walk us through the anatomy of a project using this layout. Where does everything go?
It all centers on two top-level directories that are mandatory. First, you have an include folder. This contains all your public header files. If your code gets compiled into a library to be shipped to someone else, this is the only folder they should need. It is your official API.
And then there's the implementation layer.
Yep, the SRC folder. This is your implementation kitchen. It contains all your source files, your .cpps, and any private headers that are only used inside your project, not exposed to the world.
And inside those, you maintain a mirroring structure.
This is absolutely crucial for big projects. If you have a logical module for, say, game components and a player class, you should have include gameplayer.h and a corresponding src gameplayer.cpp. That structure just eliminates confusion. It makes dependencies obvious, and it prevents those really frustrating name collisions.
Inconsistency, I imagine, is non-negotiable.
Absolutely. Clear, consistent naming conventions, usually lowercase with underscores. No spaces or special characters in funnel names, please. And beyond the source, you need dedicated directories for project health. Always, always use a dedicated build directory for generated files. This is called an out-of-source build. It means you can just delete the entire build folder and know you hadn't touched a single line of your actual source code.
And finally, you isolate your quality assurance stuff.
Your tests. They belong in their own tests directory. Keep them separate from the main source. For really big projects, you just extend this logic. You might group things into source, utility, circ-rendering, and so on.
This whole structural shift is really what defines professional software. The case study in the source material showed this perfectly. It starts with this one simple, bloated triangle.cpp file that does everything, math, input, rendering, all in one place. What happens when you apply this Pitchfork layout to that?
Your main.cpp file goes from being hundreds of lines of mixed-up logic to maybe 50 lines of clean, readable code. All it does is initialize the core engine and then call functions that are defined somewhere else. It instantly becomes a clean orchestrator instead of a giant, messy script. And that is the tangible benefit of real architecture.
Wow. We've covered a massive amount of ground today. We started by drilling into internal code quality, clarifying those 8 benefits of refactoring, including that surprising performance gain. Then we built up the scaffolding by mastering headers, understanding the declaration versus definition split, and that whole compiler linker reality check.
And we wrapped it up by putting the whole package together using the Pitchfork layout, which gives you a real roadmap for professional, scalable architecture. The main takeaway is simple, really. Quality and architecture aren't accidents. They are deliberately designed.
Okay, that leaves us with one final thought for you to chew on as you move forward. We've established that project structure is absolutely paramount for scalability. We want clean header files, a clear separation between interface and implementation.
But, and this is a big but, that separation is only valuable if the public interface in those headers is itself clean and minimal. You can have a perfectly structured Pitchfork layout, perfect folders, perfect includes, but still be hiding terrible code inside.
So what kind of architectural code smell might still pop up, even with a perfect Pitchfork structure, if the logic inside the functions hasn't been consistently refactored? I mean, what if your main header file declares 50 different functions that are only ever used by one internal module?
That's it. That is where refactoring and architecture are in a constant feedback loop. A clean architecture can easily mask internal chaos if your function's too long or your header interfaces are way too broad. That just leads to high coupling, hidden complexity. It suggests that project structure and internal code quality, they're constantly reinforcing each other. You fix one only to realize the other needs immediate attention.
And that is the next level of complexity to conquer. Keep digging, keep learning, and we'll catch you on the next deep dive.